Hello dear students, welcome back to Pen and Paper Chemistry. We continue with the topic of amines and this is part 8 where we continue with the chemical properties of amines. In case you've missed out the beginning of the chemical properties, please go back to part 7. So we've covered nomenclature, we've covered the properties, we've covered the structure, we've covered quite a lot on the channel, so please take advantage of it. Talking about the chemical properties, in the last video I had explained to you the basic character of amines and what accounts for this basic character, and we had said that because of the presence of lone pair of electrons on nitrogen, they are considered as base according to the Bronsted concept because they are proton acceptors, and this is how we had depicted it. Also, they are electron donors because of the presence of lone pair of electrons on the nitrogen, so we call them as Lewis bases. What is the quantitative aspect of this particular concept of the basic character of amines is what we are going to discuss today. Now there's a term which many students find very confusing. We are going to demystify it today. Basic character, let's relate to what we already know about basic character. We know that ammonia is weakly basic in nature, and why does it do so? Again, because of the presence of lone pair of electrons, and it combines with water to form a weak base and release hydroxyl ions in solution. So we have ammonium and hydroxide ions being formed in the solution. Same way, primary amines, secondary amines, tertiary amines, they also have an a lone pair of electrons on the nitrogen, because of which they are again able to release hydroxide ions in the solution. Look carefully. Here, the sign that we are drawing here for this reaction is an equilibrium sign, meaning to say the forward and the backward reaction are taking place at the same rate. Once equilibrium has been achieved, I can write the equilibrium constant for this reaction as K equilibrium is equals to the concentration of the products, which is the ammonium ion, and so coming from the primary amine and the hydroxide ion, divided by the concentration of the reactants, that is RNH2 and water. Here we have tried to take a very simple example. That means we've taken the primary amine into consideration. Now if you see, we are carrying out the reaction in an aqueous solution wherein the concentration of water almost remains constant because we are talking about a dilute solution. In other words, I can pick up my water, multiply it by the constant. So one constant multiplied by another constant gives me a new constant, and that new constant is what we call as Kb. So Kb is KNH3, that is the RNH3 positive, that is the concentration of the ammonium ion coming from the primary amine, hydroxide ions divided by the concentration of the amine taken initially. So we call it as equilibrium constant of a weak base. Now, if you remember, we've spoken about Ka. Now these Kb values are small, so something like 9.4 into 10 to the power minus 6. Now if you have to deal with exponential values every now and then, it gets a little difficult. So what we do is we express it as a log value. So if I take it as log of 1.6 into 10 to the power minus 19, I will get some negative value over here. So I want to convert that negative value into a positive value. So I take the negative log of this value. So in other words, I am taking negative log of Kb. Can we do that? Yes, of course. And this negative log of Kb is to the base 10 and we call it as pKb, that is the potential of the equilibrium constant of a weak base. So if you have to deal with simple numbers like 17, 6, 4.34, wouldn't that be easier? Yes, of course it is. But in the entire process, you have to remember that what you did was that you had an exponential number and you have converted into an integral number. In other words, lower the negative value, higher the positive value. Let us understand it over here. So we have over here pKb is negative log of Kb. In other words, higher the Kb value, higher is the concentration of hydroxide ions. Why am I saying so? Look at this. Hydroxide ions are in the numerator, Kb is also in the numerator. Any number is to the base of 1, to the denominator of 1. So higher the value of Kb, higher is the concentration of hydroxide ions, or vice versa. In other words, my pKb on the other hand will be lower. Basic character means there is release of hydroxide ions because these hydroxide ions are being released when electron is being donated from the nitrogen to the proton over here. So remember, higher Kb, lower pKb, and lower pKb means high hydroxide ion concentration and more basic. So pKb is more, basic character is less. More pKb, less basic character. Okay, or just draw an arrow down. pKb increases, basic character decreases. Now why am I telling you this? Because if you see, we've got data over here for pKb and we have various examples which we are going to compare and correlate it to our learning in the previous video where we classified the primary, secondary, tertiary amines with regard to ammonia in their order of basic character in gaseous state as well as in aqueous solution. So we defined in gaseous state 3 degree, 2 degree, 1 degree, whereas in aqueous solution it is 2, 3, 1 and ammonia. So now let us see this tabulation of the pKb values and various examples. Let's compare. So first one, ammonia and primary amine. So here we notice that ammonia has a pKb value of 4.75 whereas methylamine or methanamine has a pKb value of 3.38. Remember what we said just now, low pKb means more basic. So can you tell me which one is more basic out of the two of them? Yes, a primary amine. So when I'm comparing these two, I know that a primary amine is more basic than ammonia. Now let's compare methanamine and ethanamine. Look over here. Again, when I compare these two, now which of these is more basic? Look at the difference, 3.38 and 3.29. Yes, lower the value, more basic it is. So ethanamine is more basic than methanamine. You have all the reasons in place. We have discussed this, the various factors why some compounds are more basic than others. We spoke about the plus I effect, we spoke about the hydrogen bonding, and we also spoke about steric factors. So now correlate your learning to the observations to the practical observations that we see here. Now next is comparing. Let's compare methylamine and dimethylamine. In other words, I'm comparing a primary amine and a secondary amine. So what do you notice over here? What happens? Yes, a secondary amine is more basic than a primary amine. Now compare a secondary to a tertiary. Oh, notice something. 4.22 and 3.27. In other words, yes, our secondary amine is more basic than a tertiary amine as well. Remember, we are talking about aqueous solutions. Isn't it interesting? Because that's the same observation we made when we spoke about the basic character in aqueous solution. We said 2 degree is more basic than 3 degree, is greater than 1 degree and greater than ammonia. So the same logic works here and the same explanation can be given. Now what about primary and tertiary? Would you like to compare primary and tertiary? Look at 4.22 and 3.38. Ooh, my primary. So if I've got the same substituent, that means I'm talking about methyl groups here. Look carefully, 3.38, 4.22, which is more basic? Yes, of course, lower the value, more the basic character. So if I am talking about the CH3 group as the substituent, then my primary methylamine is more basic than tertiary methylamine. Okay? See here, this is what we wrote in the last video. Substituted methylamines, secondary more than primary, but primary more than tertiary. And of course, all of them are greater in basic strength compared to ammonia. And we have done a comparative account of this already. Interesting to correlate our theory to practical observation. Now, next thing we had spoken about aromatic amines. Now, aromatic amines, look at the value of pKb, 9.38. Whereas for any of the primary amines, it is in the range of 3, 4. But look at the first member of an aromatic compound, 9.38. Look at C6H5NH, CH3. That means the N-methyl derivative of benzene. What do we have? Again, 9.30. So what do you notice over here? The aromatic, the basic character of aromatic compounds is less or more? Yes, it is less than those of aliphatic amines. Higher the value of pKb, lower the basic character. Simple rule of the thumb. Remember it. So would you like to take these notes down for reference later on? As I always say, you won't be sitting watching YouTube videos all the time when you have shortage of time. Notes written in your own handwriting are always more relatable than printouts that you can easily take from the Google site Pen and Paper Chemistry. But I would encourage you, yes, it's a Google site. Just search Pen and Paper Chemistry on Google. It will show you the YouTube channel and the Google site. By the way, the earlier site, Learning Chemistry is Fun, is now closed. It has been migrated to pen and paper chemistry. So this has migrated to this site. Have you written it down? Have you jotted down the data? I am keeping it on the screen for you to copy sincerely. See, for you I am also writing it on the screen. I am writing and I am not typing it. I am writing it so that even I can recall when I have to teach you next time. So you should always correlate your experimental observations to the explanations that we give you in theory. And remember that these explanations that we have given you are given in order to justify what we are observing practically. So the canonical structures, the resonance structures. So see, these are all the explanations based on what we observe experimentally. All these notes were there in the previous video. This is something which has been taught in part 7. Now that we've spoken about the basic character of amines, let us see what basic properties are shown by amines. First and foremost, they turn a red litmus to blue in an aqueous solution. Okay. Next, all basic compounds react with acids to form salts. So we've taken the example of ammonia here. Ammonia is basic in nature, reacts with HCl to form ammonium salt. Now apply the same logic over here. Nitrogen has lone pair of electrons which it gives towards the proton. So the only difference is instead of a hydrogen over here, there's an alkyl group. So RNH3, you get a positive and Cl negative. Similarly, try completing this reaction. So from aniline, it is going to form anilinium ion. Chloride. Same way, aniline with acetic acid. Now here you see this is a weak acid, unlike HCl, which is a strong mineral acid. So I can also write it as C6H5NH3 positive. Is that right? How do we know that? This is negative, this is positive. This is the lone pair of electrons on it. And then how are you going to put the negative ion? So here it was simple, Cl negative. Here also it is simple, but you have to remember that you don't start writing CH3COO negative. Why? That would be wrong. So you have CH3, C double bond O, O negative. How can you have a carbon, this is the non-polar end, whereas this is the polar end. So how are you going to write it? As we start writing from the oxygen end of it and we try to attract it towards the positive ion. So here we will have C. It's becoming very easy now. OCO and then CH3. You can also condense it and write it as OCOCH3. Isn't it simple? So the acetate, so just like you had the chloride salt, now it's an acetate salt. As simple as that. So don't get scared when you see big formulas or when you see unknown formulas. We also know that ammonium salts, now this is a practical which you do in the laboratory, this is how you identify ammonium salts. Ammonium salts, all ammonium salts react with alkali, strong alkali, for example NaOH, to give you what? Can you tell me? Yes, a pungent smelling gas, and that pungent smelling gas is ammonia. The same principle applies. And what are the side products? You've got the salt and water. The same fundamental applies to amines as well. So they also react with strong bases but they will release the corresponding amine, because here I will have it as RNH2. So look here, RNH3 positive, Cl negative. So that means my primary amine salt reacted with a strong base to give me back the primary amine, salt and water. Isn't it easy? Go ahead, you can add it to your notes, which you must be making by now. There we go. In the next video, we shall be starting with nucleophilic substitution involving primary amines. So don't miss that video, because we will be doing quite a few chemical reactions and the behavior of amines. Stay tuned, stay connected. See you in the next video.